Okay, so today I'm going to read to you or introduce to you dolomites and dolostones, uh, a unique section of carbonate rocks, and it's mostly related to diagenesis, so it's very good that you learn about this material. So dolostones, you might have met the term before, and dolomite, you might have met them before. Dolostones refer to the rocks, and they're chiefly composed of dolomite, the mineral. And you might remember that this is calcium magnesium carbonate. Now, most of the dolostones that we find in the rock record are thought to have been produced through the diagenetic process, and in particular the diagenesis of limestones. Now, these dolostones, they can have the same textures as are found in limestones. They can be fully dolomatized or they can be partially dolomatized. And fully dolomatized rocks don't have grains in the sense that we talk about grains as allochems, but rather they would have crystals. And usually they have less fossils than limestones and certainly less pristine fossils than limestones because all of these fossils or allochems or whatever species are being preserved tend to be destroyed in the diagenetic process. So let's look at crystal lattice and the arrangement of irons that would make up a high magnesium calcite versus a poorly ordered dolomite in the middle, and then finally stoichiometric or fully ordered dolomite towards the end. And these are the key things: the calcium being the blue, the magnesium being the red one, and you can see that they're similar size based on where they fall on the periodic table. Then we have our oxygen, which is this yellow ball, and then a tiny carbon. Now you can see the carbonate species is surrounded by the three oxygen. The carbon and the three oxygen make up the carbonate, and this is common through all of the different species. And what's different on all of them is the arrangement and the abundance of the magnesium. All right. So in high magnesium calcite, you have some random magnesium coming in and taking the place where calcium rather would be. And it tries to alternate, but it's not making one complete layer yet. It's nowhere near. When we get to poorly ordered dolomite, it's making these alternating layers. As you can see here, it's almost complete one layer. This one is out of place, and this one is an almost complete layer, and this one is nowhere near, but it's on its way compared to the high magnesium calcite. So this is poorly ordered dolomite. And on the right, where we have the stoichiometric or fully ordered dolomite, you can see the top layer plane has completely been replaced with magnesium, and so this is all magnesium. And then you have calcium, and it's all calcium. Then you have the alternating layer, all magnesium again, and then all calcium. So this is what they call stoichiometric or ordered dolomite, which is what we find in a lot of the diagenetic dolomites. And we don't find this forming naturally on Earth surface temperatures. It's very rare to get this very ordered stoichiometric dolomite. And because of this ordered nature is one of the difficulties why we don't have dolomite precipitating primary as primary minerals. And we're going to talk about this some more. So dolomite is a mineral, although in some books you will see them called dolomite the rock, or some articles, research articles, you'll see them called dolomite the rock as well. We more or less use it interchangeably, but some people are sticklers for terms and terminology, and they say dolostone is the rock and dolomite is the mineral. I believe I can't help myself. I use them more or less interchangeably, but dolomite typically is the mineral, and dolostones typically represent the rocks. So the rocks are composed of dolomite, the mineral, and they should be called dolostones. And dolomite is now forming only in a very few modern environments, yet it is widespread in the geological record, and this has been a big question for a long time. Now, the current view about the formation of dolomite is that primary dolomite is rare and that most dolomite is of replacement origin, meaning that they came about during either early or late burial diagenesis. Now, for dolomatization to occur, and dolomatization is a term that we use to say that limestone went through a specific kind of diagenesis to produce dolomites. So, for the process of dolomatization to occur, we need a source of magnesium, and the source is normally marine water. And this is because high magnesium calcium ratios favor dolomatization. So, if you have way more magnesium, then you will likely it's going to be possible to get dolomites forming. A mechanism also is necessary for pumping this seawater or this magnesium rich water through the limestone to facilitate the diagenetic dolomatization. Now, seawater is generally supersaturated with respect to dolomite, but because of kinetic factors, dolomite is not being widely precipitated, and these kinetic factors include: one, the high ionic strength of seawater and fast carbonate precipitation rates. Additionally, dolomite is highly ordered, the mineral which I was showing you when I was showing you the atoms and the ions and so forth. And this means that it has a regular spacing of calcium and magnesium ions and that alternating spacing. And this takes a long time to form. And what happened is that the dolomite cannot get ordered that fast or fast enough, and hence calcium carbonate is precipitated and not dolomite from the seawater. The hydration of magnesium ions. So the magnesium ions tend to be associated with the water molecule being hydrated, and as a result, the calcium ions are more readily absorbed into the crystal structure, and calcite or aragonite tend to form more easily than dolomite. Magnesium hydration, though, can be overcome by higher temperatures, and that's why burial dolomatization is so popular, because once the sediments are being buried, the temperature increases, and so the hydration is broken up, and the magnesium can now be unhindered and fit into the lattice and take up the spaces that they need to take up to get these ordered dolomites. And then the other ionic issue or kinetic factor is the low activity of the carbonate ion. Now, seawater mostly contains bicarbonate and carbonic acid, not necessarily a carbonate naked ion floating around. Now, dolomite forms from the carbonate ion and not the bicarbonate anion. Therefore, high alkalinity and high pH solutions favor dolomite. So when you have that reduced acid, then you get it, right? And this is one of the reasons why diluting seawater with fresh or meteoric water reduce the kinetic factors, because the resulting solution is going to be less concentrated. All right, so in order to understand dolomites, you definitely need to know what they look like in thin section. And so we're going to jump into the description of the actual crystals, what they look like, what they call them, and how to identify them. And it's going to include a discussion about staining. The most diagnostic thing to recognize dolomite is the rhomb shape. Maybe I should take off the rhombohedral because it's not quite rhombohedral, but there's rhomb or diamond or kite shape mineral, right? And they commonly, sometimes they have inclusion rich cores, so that makes them dark and cloudy on the core, in the core part of a diamond shape, and clear margins, and the latter is often attributed to cementation. So clearer margins and these cloudy interiors, clearer margins and these cloudy interiors. I think this is an exceptionally odd case, but I'm gonna show you some other pictures and that might help. Okay, so Sylvia and Greg in 1987 presented a classification for dolomites, and their classification scheme consider the crystal size and the crystal boundaries. So they basically group them into two groups, unimodal and polymodal. In unimodal dolomite, all the crystals, as you can imagine, are the same size, and in polymodal dolomite, the crystals have different sizes. Then, in addition, they talk about crystal boundaries. The boundaries can be planar or non-planar. In planar dolomite, the crystals are either euhedral or subhedral. So some texts refer to it as planar E, euhedral crystals with high porosity, or planar S, where you have subhedral crystals and lower porosity. In non-planar dolomite, the crystals are anhedral. So this is just a basic classification, and it's quite easy to remember. Planar, non-planar, planar E, planar S. Okay, the nucleation rates. I think this is very important for us to talk about. Now, the nucleation of dolomite crystals is favored by high surface area to volume ratio. Thus, finer grained carbonates like micrites will have greater nucleation rates than coarser grained carbonates. Therefore, primary difference in grain size, for example, allochem in a micritic matrix, will lead to polymodal dolomites because of the difference in nucleation rates. Whether the size distribution is unimodal or polymodal is determined by the nucleation and the growth kinematics. In theory, coarser dolomites should develop at higher temperatures and finer dolomites at lower temperatures, with everything else being equal. Unimodal size distributions will form where there is a single nucleation event, or where there is uniform distribution of nucleation sites, or where there is uniform growth. If these conditions are not met, then polymodal dolomite will form. Supersaturation of dolomite. At low supersaturation, faceted crystals or planar fabrics form by spiral addition of molecules. At high supersaturations, molecules are added randomly and non-planar fabrics are created. Now that's quite interesting. So the fabrics can tell us something about the environment. Now, when it comes to the dolomatization of polymorphs, dolomatization of different polymorphs will develop at different rates assuming the grain size. Aragonite is going to be preferentially dolomatized in comparison to high magnesium calcite and low magnesium calcite. And high magnesium calcite is going to be preferentially dolomatized in comparison to low magnesium calcite. And this is quite interesting because it's following the same category of how aragonite, which one is more stable versus which one is most stable. So calcite is most stable, so low magnesium calcite is going to be less preferentially dolomatized than high magnesium calcite because that one is less stable than it, right? So it's the same concept that we learned earlier. Another term that I want to introduce to you is mimic and non-mimic dolomatization, or two terms rather. Now, in mimic dolomite, both the form and internal structures of allochems are preserved, and this requires high nucleation rates. In non-mimic dolomite, the forms may be preserved by lines of inclusions or ghosts, and this is due to low nucleation rates. Although one exception is the echinoderm grains, because they're single crystal, no low nucleation rates will lead to mimic dolomite rather than non-mimic dolomite. Typical textures. Lime mudstones are commonly dolomatized with a fine-grained dolomite and the retention of sedimentary structures, and this is due to the high nucleation rates in micritic grade sediment. Many dolostones are, however, composed of coarsely crystalline dolomite, often called sucrose dolomite. Sucrose from sugar, and this is how these grains or these rock tend to look like it's made up of cemented sugar. And that's why they get that name. Now, this results from lower nucleation rates and low supersaturated growths to produce this unimodal planar E dolomite. So all of the crystals have the same size, just like if you had a cube of sugar, and that's what the rock. looks like in some sort of exaggerated way. Next term that I want to introduce to you is saddle dolomite. Now, dolomite cements may form in cavities formed by dissolution of unstable grains prior to dolomatization. And these dolomite cements are non-planar and have a rounded crystal boundary. And they are commonly called saddle dolomite or baroque dolomite. So let's look at what these look like. Now, this is a simple version that I took from a text, and this shows non-planar fabrics being all these anhedral grains on the left, or anhedral crystals rather, on the left, and then on the right we have the planar fabrics having planar euhedral with those nice flattish euhedral edges, rhombs, and other shapes. And then we have planar subhedral where you have nice smooth flat edges on some sides, and then the other sides have lots of junctions, and so the edges are not that smooth. So that's a nice simple one, very easy to remember, and if you sketch that in an exam it will be fine. And then we have another one that I took from a text, which is a little bit more complicated with some higher names, and I want you to look at these as well. And so on the left we have planar idiotopic dolomite, being these euhedral forms for the most part, and they're broken down into planar euhedral, which is similar to what I showed you on previous slides, having most of these crystals having these nice euhedral shapes. The crystals tend to be supported with intercrystalline areas filled with another mineral or porous. Then we have the planar subhedral with these compromised boundaries. Then we have planar void filling euhedral dolomite crystals lying in large pores and vugs. And then we have these planar porphyritopic type floating in a limestone matrix. So you see these nice diamond shape or ram shape or kite shape crystals just precipitating or recrystallizing in the limestone that is existing there. Now on the right we have the non-planar dolomite, and we have tightly packed anhedral grains or crystals. Most of them are curved, oblate, or serrated, indistinct, and they tend to have undulatory extinction. Then we have the non-planar void filling or baroque type dolomite, and you can see they have this pointy termination. They tend to have sweeping extinction, and they tend to have also this cleavage, curved cleavage, and curved edges sometimes. Then we have non-planar porphyritopic type, where we have single anhedral dolomite crystals or patches of anhedral dolomite crystals floating in a limestone matrix, and these also tend to have undulatory extinction. So let's look at a preservation pathway. We can start with our carbonate grains. They can become unreplaced. You can get molds. They can become partially replaced or fully replaced, and then you can have either mimic, meaning that you can see all of the carbonate grains but they have a different final mineralogy than when they started out. They would start with aragonite or calcite mineralogies, and now they have dolomite mineralogies. Or you can have non-mimic, where the form internal and external forms are not preserved. The matrix can be unreplaced or partially replaced or fully replaced. The void filling can be unreplaced, partially replaced, or fully replaced. So what does this look like? So we have our original wacky stone here, some micrite in between, and we have all of these allochems, right? So we have different nucleation, and you can see little floating crystals of dolomite coming in, growing, right? And here we have polymodal planar S dolomite with replaced bioclase. So the original forms have been replaced, but you can see them. You can still say, guess what that is. You can still say that this is a bivalve shell, and so on. Then we have unimodal planar S dolomite here with voids after bioclase. So you can see the bioclase have been dissolved. Then we have unimodal planar E dolomite with intercrystalline porosity. And you have ghosts. Maybe you can barely see them. Or you have unimodal planar S dolomite with little porosity. So this has no porosity. You can see the pore spaces in between these crystals on the left. No porosity, but you might have these ghosts of the forms or shadows of the allochems that were there in the past. So this we would call mimic, and this one would be non-mimic. Non-mimic. So we have different crystal sizes here, so we'd call this polymodal. And because not all of the edges are nice and smooth, we will call this planar S for being planar subhedral. And these, we have some pore spaces in here. You could call this most of them are the same sizes, more or less. Planar, unimodal, planar S. Polymodal, different sizes, planar S with calcite matrix. So the dolomite is very light colored. It is unstained, and calcite stains red when we put a particular staining on it, and that's why we have these red and these oranges. So all of the red and orange is calcite, and all of the clear stuff is the dolomite crystals. So we have dolomite crystals here. They're very fine grained. If you were to put it on high magnification, you would see that they're polymodal and they're all euhedral. But we have these black spaces in between, and some of them are actually porosity. And so there's intercrystalline porosity in here. Okay, so on this slide we have a crystal, and this is a void filling baroque or saddle shaped dolomite, and you can see it right there. From our staining we can also get blue colors, and you can see that this blue color is within the crystals for the most part, and that's blue staining of dolomite. Now, dedolomatization is another term that I want to introduce to you, and this is the reverse process to dolomatization, and it's brought about by reactions with fluids with high calcium magnesium ratios. So that would be the opposite type of waters that then would cause dolomatization in the first place, because dolomatization prefers fluids that have a high magnesium calcium ratio. So this is opposite, a high calcium magnesium ratio. Now, this process only occurs near the Earth's surface and is therefore an indicator of near surface diagenesis, possibly as a result of uplifted dolostones. So here on this photomicrograph, we can see red calcites and unstained dolomite rhombs, but inside of them they're changing to calcite. You can see the rhombs are changing back to calcite. And here, a similar scenario. So how do we classify a carbonate rock as dolostone or limestone? This is going to be based on the proportion of dolomite present. So if there is 0 to 10% dolomite present in a carbonate rock, then it's going to be a limestone. If you have 10 or 11 to 50%, then it's gonna be a dolomitic limestone. If it's 50 to 90% dolomite, then it's gonna be a calcitic dolostone, and if it is 90 to 100% all dolomite, then it's going to be a dolostone. So what we have a lot of is dolomitic limestones. We have a lot of limestones, and we also have a lot of calcitic dolostones. Very rare you get 100% dolostone for an entire formation. Formation maybe some sections will be limestone or calcitic dolostone, and then other sections will be dolostone. So how can we get these dolomatization occurring? Now, depending on what you read, you'll see a whole bunch of different models. But more or less, there are 5 main models accepted for simplification. Some books you'll find up to 30 different models depending on what they found and how they can differentiate the particular situation and scenarios. But again, for the purposes of this lecture, we're gonna just introduce it to 5 broad categories, 5 broad models, and these are the evaporative model, the seepage reflux model, the mixing zone model, the burial model, and the seawater model for dolomatization. The first one is the evaporative dolomatization model, and this model is a classic example is found in the Arabian Gulf sabkas. And the sabka is that environment in the coast, on the coastline, in the supertidal zone, really, where it's very hot. So desert beaches and storms will recharge the sabka with marine water, and evaporation of this marine water occurs because the area is arid, and this promotes the pumping of groundwaters. Now, in this area, you get the very fast, quick precipitation of aragonite and gypsum occurring on the sabkas. And this quick precipitation from the evaporation causes a high magnesium calcium ratio, and either primary dolomite is precipitated or aragonite is dolomatized, especially when the additional calcium produces more gypsum. Now, we will consider evaporite deposits in a later lecture, so we'll talk about how gypsum is formed next time, so don't worry about that right now. So this is what it looks like. This is the coastline, this is the land, this is the supertidal zone in here. The storm splashes up a lot of water in this area. There is evaporation, the gypsum and the aragonites are precipitating. The gypsum is taking out the calcium, so there is high magnesium because the gypsum is removed, which removes the calcium, and so higher magnesium is left in the solution, and then the magnesium goes into the aragonite or precipitates and forms dolomite crystals primarily. The next model is the seepage reflux model. And the typical example of this model is the Carlsbad limestones of Texas in the United States of America. Now, the Carlsbad limestone represents a back reef limestone setting, and that limestone has been dolomatized while the Capitana Reef is not dolomatized. So what you have happening here is the precipitation of gypsum in the lagoon, and this increases the magnesium calcium ratio because to precipitate gypsum you're taking out the calcium, and this causes the water or the basin to become more supersaturated, so it forms a brine, and the brine is very dense and it seeps into the back reef limestone and causes a sort of reflux, and this is caused by salinity differences, and so the fluids are getting pushed towards the sea through the reef, and so that is a pumping mechanism which results in the dolomatization of the back reef area because that's where the highest magnesium stops and gets into the lattice. And the front of the reef remains undolomatized. So this is it here, and all the XX shows where you have the dolomatization, right? So the basin is evaporating, it's getting recharged. There's a pumping of the waters from the restricted basin through because of salinity difference. If it's, this is very saline, highly saline, and the water is going through there, through here, and of course the magnesium dolomatizes the reef, limestone reef here, and the front of the reef is undolomatized. So that's all of what I just said. The high magnesium calcium ratio fluids are generated in lagoons and beneath tidal flats and subcars via evaporation. They descend to the subsurface due to differences in density, contrast with the marine pore waters, and this model is frequently applied to dolomites associated with evaporite deposits. The third model is the mixing zone dolomatization. And a typical example is thought to be the Hope Gate Formation, which is a quite popular formation on the north coast of Jamaica. So if you ever went to the Discovery Bay Marine Lab, especially if it was on a geology excursion, you might have seen the Hope Gate Formation. And the Hope Gate Formation is fully dolomatized. And dolomatization is possible in this model because the dilution of seawater by meteoric water overcomes the kinetic factors that oppose the formation of dolomite from seawater. So what you have here is the Hope Gate Formation for schematic purposes, and you had a higher sea level that caused it. This was forming the Pleistocene time, and the sea level fell, and so you have the migration of the mixing zone. And so when you have that migration of the mixing zone, the water becomes diluted and some of the kinetic factors are removed, and the magnesium goes into the section, and all of that section is dolomatized. Now, the mixing zone model is popular with relatively early near surface dolomatization, especially when there are no evaporite associated. Now, it is felt that the mixing of meteoric waters with up to 30% seawater would cause undersaturation with respect to calcite, but increased saturation for dolomite. The precipitation thus occurs where salinity has been reduced, but a high magnesium calcium ratio is maintained. The fourth model is the burial dolomatization. Now, here we have compactional dewatering of basinal mud rocks, and these release magnesium-rich fluids. This model suggests that these fluids migrate into shelf-edge carbonates, increasing the magnesium-calcium ratio, and this causes dolomatization. So if you will look on this schematic, you will see that throughout diagenesis, sediments are being buried. As the sediments get buried, magnesium fluids get pushed up and migrated, and they go in and fit in where they can in the lattice of limestone, and then that limestone converts to dolostones. The driving force is compaction of basinal mud rocks and the expulsion of magnesium rich fluids into adjacent platform limestones. The magnesium fluids are thought to be derived from clay minerals in this instance. Now, increased temperature of the burial environment should mean that some of the kinetic obstacles that would prevent dolomite precipitation would be overcome. However, problems arrive in that there's sometimes not a continuous source of fluids. Although hydrothermal fluids may circulate through faults and fractures, and in this instance, they can cause dolomatization. And a thing I didn't remember to mention was that the baroque crystals, or those saddle-shaped dolomites, tend to be associated with hydrothermal fluids, and so that might be diagnostic in some instances. And the fifth model is seawater dolomatization. Now, the classic example of this kind of dolomatization is Eniwatok, atoll in the Pacific Ocean. Here, dolomatization is caused by the efficient, and I put efficient in quotations when I'm talking, but you can't see that. Efficient pumping of seawater through carbonate sediments. And there are no other mechanisms that could explain the occurrence of dolomite in this instance because there is no fresh water on this atoll. There are no evaporites forming, and so they say, okay, it must be the effective pumping or the efficient pumping of seawater to form these dolomatization. So magnesium source is from the seawater and it's pumped through sediments by ocean currents from some sort of convective activity due to differential temperatures of the platform where you have these warm waters and then the open ocean you have cold waters, and so there is constant circulation, and that circulation is quite effective to supply a constant supply of magnesium to go into the lattice and to change these limestones or calcites and aragonites for the corals, which are mostly corals tend to be mostly aragonite, and so all of those aragonites get transformed to dolomite, the older stuff, right? All right, so very critical. We have to talk about staining, carbonate staining, and the making of acetate peels. And this is a technique that you might find quite useful, especially if you study a lot of carbonate rocks and you do need to quickly identify them without expensive elemental studies. So carbonates can be studied in thin section, and the use of acetate peels can be quite quicker and cheaper than thin sectioning, and they can often give very valuable results. Now, the staining that we're going to talk about is something that is popular in geology, not just for carbonates, although you probably will only see it for carbonates, but they also have a staining technique to differentiate minerals that are similar, such as feldspars. I do believe they have a staining technique for feldspars, but today we're going to talk about carbonate staining. So when I talk about staining, remember that it's specific to carbonate minerals. Now, if you're going to make an acetate peel, I'm teaching you two things today: how to make acetate peel of a carbonate rock and also how to stain your carbonate section or the mixture to stain the section. So now we're talking about the peels. Now, the surface of the rock to be investigated is sawn and polished to give a good surface. You polish it in the same way that you would polish a rock to put on a slide. You polish it with your silicon carbide with water. Then the surface is etched with a dilute hydrochloric acid, typically about 5% solution hydrochloric acid to distill water, and then you leave this rock to dry. Maybe 5 minutes or so. The surface then is slightly tilted from the horizontal and flooded with acetone. A sheet of acetate paper is carefully lowered onto the surface, and while it is still wet with acetone, and the sheet is left for 10 minutes until the acetone has evaporated and is dry and nice and comfortable. And then the sheet is carefully peeled from the rock and mounted between two glass slides to preserve it. So these are some acetate peel that I had on some rocks. So you can see it's a clear film of plastic on the rock, and then I would just rip those off, and once it's ripped off, the complete peel or finished acetate peel will now contain a representation of the fabric. So all of the grains, all of the shapes, and all of that preserved. And you can do count or pick out the cements different from the allochems and all of that, and you can make quite a bit of them really quickly, certainly much faster than it would take for you to make a thin section. And you can look at it under a microscope and you can do grain counting and you can identify allochems and a whole bunch of stuff that might be very useful. Now, staining is another technique to help. And before we talk about the staining, we want to talk about the iron content of carbonates. Now, under reducing conditions, iron and a variety of them, the 3 plus or ferrate, can turn to Fe2 plus, and Fe2 plus is going to be similar to magnesium 2 plus or calcium 2 plus, and so it can be incorporated in the lattice of calcite or dolomite. Now, these produce ferro calcite or ferro dolomite, meaning that they contain iron, and these may contain up to about 2% iron, and as a result, skeletal grains or cements forming in oxic environment will be non-ferro calcite or dolomite, while cements and neomorphic textures forming at depth in reducing environment will be ferro calcite or ferro dolomite. And so we have normal calcite, normal dolomite, normal aragonite, normal high magnesium calcite, and all of these different things. And we need to be able to differentiate them. And this is where staining comes in. And the various compositions of calcite and dolomite can be distinguished by using the stains. Now, there are quite a bit of different staining methods or different staining solution, but a popular method is called Dixon's method. And the Dixon's method is a mixture of several solutions. So in order to make the Dixon's method of stains, you want to make sure to use our rubber gloves because some of the ingredients are quite poisonous. So to start with, you will need etching solution, which is 1000 ml of 1.5% hydrochloric acid. Then you will need 0.2 grams of alizarin red, and you can dissolve that in 100 ml of your 1.5% hydrochloric acid. So the same etching solution, you can take 100 ml from that, and you can mix that in a test tube or a beaker. Then you can weigh out 2 grams of potassium ferricyanide crystals, and you can dissolve that in another 100 ml of 1.5% hydrochloric acid. Then, in order to make the stain, you want to use 3 parts of alizarin red. So if you use 30 mLs, then you would use 2 parts of potassium ferricyanide, so you would use 20 mLs. If you use 60 mLs of alizarin red, then you would use 40 mLs of potassium ferricyanide, and so on and so forth, depending on how many rocks you're staining or how many thin sections you're staining. And once you mix that together, you have your Dixon solution. So how do you stain? Again, you're going to be making sure that you have on rubber gloves, good quality rubber gloves. And if you're staining a rock, like a rock that you're going to use for acetate peeling, you can cut and polish that rock surface. And then you want to etch the surface with 1.5% hydrochloric acid. And then you're going to immerse the surface in combined solution for 30 to 45 seconds. Then you want to wash the surface with distilled water, not tap water, which may contain cations and anions and might discolor it. So you want to wash it with distilled water. And you can produce an acetate peel before, and the acetate peel will have all of the color and all of the grains that attract color. And the calcite is going to be pale pink, and it might transition into red. The ferro calcite can be mauve, purple, or royal blue, and the intensity of the color increases with the iron content. The dolomite will remain unstained, so it will have no color, and the ferro dolomite is going to be pale turquoise to deep turquoise. And again, the intensity of the color increases with the increase in iron content. And you can view the peel under the microscope, and if this is with a thin section that you stained, you can also see the colors under the microscope. So remember earlier in this course when we saw all these colors and I told you, all that was staining and that meant that it was calcite, or all that was staining and that meant that it was dolomite, ferro dolomite, or you remember that blue dolomite that we saw. So you can know that it helps to identify the mineralogy. So this is a section that I had, and these are clastic grains, and you can see they remain unstained, and all of the cement in between are red, and this is calcite cement. You can see a very dark rim of cement around the grain. So this is calcite cement. So it's very good to see all the diagenetic features. So we have this micritic rim here, and then we have this micrite of calcite, and then the class remains unstained. Here we have another section, and the cement in between is all red, and then the class tend to be unstained.